we're good. So yeah, go questions and such, and then go through asterisk, ampersand, all of those C things, including this arrow. And then with that, go ahead and talk about ODP 205, which posted this morning. And then probably tomorrow get into pseudocode for linked lists again, but using this language and sort of thinking at a higher level. So questions. And the bar is high. We spent about 35 minutes in the previous section answering questions. So.
Can you go over the new ODP?
I can go over the high-level view, and then we can get into specifics here.
Can you kind of make it we can do two different programs at once?
Say sorry?
Do you
Sorry?
want to do it? You can do two different programs at once.
Can you, what do you mean?
Like when you're writing the actual ODP versus looking at the README.
Oh, yeah, I wasn't going to write the ODP. I was just going to look at the README.
No, but I mean for when I'm actually making.
Yeah. Oh, how do you just pop in 2 times, open another putty session or something?
Okay.
That's the easiest way. Or, copy it and paste it into a Word document or something. Do something just so it's like persistent. So 205, this is not part of PA1, okay, but it's a warm-up for PA2. It's not part of PA2 either. It's a practice with working with pointers to nodes. So we don't have an array of struct nodes anymore, okay? We're just dealing with a function called set that takes a single argument which points to one struct node, okay? So the argument is a pointer to a struct node. It's not an array though. Okay, it's really just pointing to one node. Can you see this from? No? All right. Well, don't fall asleep. But all right, does that work?
That's it.
Yeah.
Okay. All right, so your goal in this ODP is to write a function named set. It returns void, so there's no return value. It takes a single argument, which is a pointer to a struct node, and it does 2 things. So a struct node has 2 fields, a data piece and a next piece. Data is an integer, and next is a pointer. So what it should do is double the data value and then set the next field equal to null. And it's no longer my null, it's just null, N-U-L-L. All right, so to do this, we need to be able to get to these fields. So here's a struct node. As an integer data. And a struct node star next. So I'm just going to call the argument arg. So it's something like void set struct node arg. And so this syntax says arg is a pointer to a struct node. All right, so if arg is a pointer to a struct node, how do we actually express the node that it's pointing to?
We assigned it to something.
Even without assigning it, how do we refer to the thing that arg points to? Or any kind of pointer. If we have a pointer to an integer, how do we refer to the integer to which it points?
Dereference it,
Dereference it. So how do we dereference?
put the star in front.
Put the star in front. So arg is a pointer to a struct node. Okay, star arg is the struct node to which arg points. And that's called pointer dereferencing. So anytime you have a pointer, you can put a star in front of it and say, I want the thing that that pointer points to. If p is a pointer to an integer, star p is the actual integer that it's pointing to. So in this case, star arg is the struct node that this argument is pointing to. Okay, well, a struct node has two fields. It has a field called data, and it has a field called next. So how could we get to the data field of the node that this is pointing to? Star arg dot data. So I'll make this a comment too, is the data field of that node. And everything we do PA2 on, almost everything we do, we're going to be dealing with pointers to structures instead of structures themselves. We're going to be dealing with pointers, we're going to be passing pointers, returning pointers. It's always going to be a pointer to a structure. So if we want to get to the data field, we're going to have to dereference the pointer and then pick up the data field. So if we want to double the data field, what would that look like in code? Exactly. Star arg dot data equals star arg dot data times 2. So that'll double the data field. And if we want to set the next field to null, it's just that.
That seems deceptively simple.
It's going to get even simpler. But yeah, that's all there is to the ODP, basically. All right, this is fairly ugly, though. This parentheses star arg close paren dot data. It works, and you can write this, and your ODP will work correctly. But it's not ideal. That's where the dash greater will come in. So let me show you what's going to happen. We're going to have a node. So let's call this previous. And let's say this points to another node. And let's say we want to know what the data value of this next node is. And everything's a pointer to a struct node. So we have struct node previous. Okay, if we wanted to get to this data value of this following node, what could we do? We could say something like struct node current, and then we could say current equals thing that previous points to dot next, and then we could say the data, which is what we're looking for, equals thing that current points to dot data. And that's going to set the data equal to whatever's stored up here. if we tried to write this without using a temporary variable current, because we're only using current so we can get to the data field of current, this is what this would look like. The data equals, well, let's take the thing previous points to. Let's pick off the next field. Let's take that's current. Let's take the thing that points to, and let's pick off the data field. All right, and that's not a fun thing to write. Well, it is kind of fun to write. I like it, but that's fairly complicated and error prone. And as we go further and further, if we wanted to pick off the data field from the node that this points to, where this is the node that points to, right, this is just going to get wider and wider with more and more parentheses. Okay, so there's a different way to do this. So if we have a pointer and we dereference it and we access a field, this can be written differently. It can be written as pointer, a dash and a greater than, so it looks like an arrow, and then the field name. And that's the syntax we're going to stick to. We're not going to write things like this or that. We're going to use this arrow notation, and we're going to think of this as kind of like PTR dot field, right? If pointer was actually a node, we could say pointer dot field to pick off that field. But since pointer is pointing to a node, instead of saying dot, we're going to say arrow. And in my brain, I think it translates as like the thing that pointer points to dot field or something like that. But here's why we want to do this. Because now this would just be current equals previous arrow next. And this would be the data equals current arrow data. And if we try to do this without the temporary variable current, what does this look like? The data equals, well, current is just previous arrow next. That gives us current, and then we want to access the data field. And once you're comfortable with this, this should read to your brain as, okay, take previous, look at the next field, that points to something, pick off the data field of that next thing. So previous points to here, that's next, there's the data field. And we can string together arbitrarily complex. We can take the thing that this points to, and the thing that points to, and the thing that points to, and it's just going to be a bunch of arrows. And it'll be really nice when we're working with things like trees, where we have multiple pointers on each node. And this will just make things a whole lot smoother. So for ODP 205, right, write it like this, because if you understand dereferencing, right, this is the struct node, this is the data field. Go ahead and write it like that. Assess it, get your full credit, but then try changing it into using the arrow notation and see what your code looks like, and it should come out looking a little bit cleaner. If you do that and you can't get the arrow notation to work, right, go back to that older version and assess that so you get 100%, because it records whatever the last assessment was. So save this code, and if you can't get this to work, just reassess the version that you had working before you stop. Okay, but it's a way to sort of like work with this and see if you're getting it right. And once you've written this a few times, 5-10 times, it'll be pretty natural. It starts to feel like this is actually doing what it looks like it's doing to you. All right, so the rest is boilerplate, right?
What does the ampersand do?
Yeah, so that's boilerplate, right? Build your test bed and assess in the usual way. Boilerplate means it's the same again and again and again. So this last part of all of these readmes seems to be the same for now. Building a testable image and assessing and so on. Boilerplate is like when you look at an end user license agreement, a lot of the language in there is common no matter if this is Facebook or Google or Imager or whatever else. It's the same stuff. It's just stuff that has to be in there. All right, so what does the ampersand do? The ampersand is kind of the opposite of a star. So ampersand variable means the address of that variable. Star pointer means the thing at address pointer. So here's our memory. So let's say location 10 is where we're storing the variable I. And let's say location 20 is where we're storing the integer j. And let's say location 30 is where we're storing the integer star PTR. So this is location, this is what we're using it for, and this is the contents. This would be a really good midterm question. So our code says pointer equals address of I. So what's going to change in our memory? Is anything going to change, or is it just going to ignore that statement?
Integer I is going to be the address of the pointer.
Other way around.
Pointer is going to be the address of I.
Pointer is going to be set equal to the address of I. So what's the address of I? 10. And where is pointer stored? Stored at location 30. So this instruction is going to put a 10 right in here. Pointer is stored at location 30. So I is at 10, J is at 20, pointer is at 30. And I've just put down the types of each of these things. So pointer is a pointer to an integer. I and J are just ints. So this says take the address of I, that's a 10, and store it in pointer, which is at location 30, so it's going to put a 10 right here in memory. Okay, now if I say I equals 5, what's that going to do to our memory? Yeah, so where's I stored? Location 10, so that's going to write a 5 right here. All right, J equals star pointer. So what's the CPU going to do with that?
Store
Store the address of pointer in
J equal I.
Store the contents of pointer in J.
Almost. Your first 4 words were perfect. So pointer is a variable. Star pointer means the thing at the address that is in pointer. Let me write this differently. Means the thing to which PTR points. So PTR is equal to 10. Star PTR means the thing to which PTR points, the thing at address 10. So what's at address 10? It's a 5. So this says set J equal to 5. And where is J stored? It's stored at location 20. So this is going to put a 5 right here. This is just a fancy way of saying J equals I.
That's what I say.
All right, pointer equals address J. What's that going to do? Say again? So what's the address of J? All right, so J is 5, but the address of J is 20. So this says pointer equals 20, and this is where pointer's stored, so that's going to put a 20 right here. All right, star pointer equals star pointer plus 1. So how does that play out?
J becomes 6
J becomes 6. Why?
because the thing that pointer points to gets incremented.
Okay, so pointer is 20. Star pointer is the thing to which it points. That's this 5 right here. Add 1 to that, that gives us 6. Star pointer is the thing to which pointer points. That's this location here. This says set that location equal to 6. And this is just a convoluted way of saying J equals J plus 1. Why is it incrementing J? Because we set pointer to be the address of J. All right, pointer equals star pointer. This will bake your noodle.
Change the 20 to a 6. I equals 6.
Yeah, star pointer is the thing that pointer points to. Well, pointer is 20, so the thing it points to is a 6. Set pointer equal to 6. Changes this to a 6. One more. I equals star pointer. What is that gonna do?
I know because we don't know what 6 is.
We don't know what 6 is. This says go to the location that pointer is pointing to. Pointer is 6, go to memory location 6. Whatever value you find there, store that in I. This will either load some arbitrary value into I, or it will segfault. Because it's possible memory location 6 is not accessible to us. So it could give us a segfault, could give us random numbers. Could give us a random number, and the next time we run it, it gives us a segfault. Because it depends what's going on with memory location 6. Is it accessible, and what's stored in there if it is? And there's nothing just from kind of eyeballing this that says, hey, I'm going to get a seg fault when I get down here. Okay, it's only known once you sort of know what the values are and you go through this. All right, so star and ampersand kind of do the opposite of each other. Not opposite, but they kind of go in different directions from one another. So I is equal to 5. If we say star ampersand I, what are we asking for besides trouble? What is
ampersand? Same thing as asking for I, or
it's the same thing as asking for I, because ampersand I is the address of I, and star anything is the thing to which this points. Well, ampersand I points to I, so star ampersand I is the thing to which a pointer to I is pointing. That's just I. So this is a fancy way of saying I. Theoretically, this is going to do the same thing. Take the thing to which I points and then find the address of that thing. That's just going to be I. But this may seg fault. Because in order to evaluate this, first it has to find the thing that I points to, and if that's pointing to a location in memory we can't get to, we'll get a seg fault. So theoretically, this would also be equal to I, but in practice, maybe it is, maybe a seg fault. And we can do all kinds of things. We won't today, but well, maybe we will. Yeah, let's do another. I'm making this up as I go, so you know it's going to be bad. So let's do I equals 100. So that's just going to store 100 in here. And then do J equals address of I.
Is it a star pointer?
It's a yes, but let's not worry about it. We'll be sloppy programmers for a minute. It's just an integer. The compiler will give us warnings, but we're going to ignore it. So I is 100, J is the address of I, so what happens to J?
J is 10.
J is 10. Okay. Pointer equals address of J. So that puts a 20 in here. So plus plus star star PTR. So what is this going to do? It's a weird one, right?
What's plus, anyway?
Plus plus is an increment.
Oh.
Close. So I've got 2 stars in front of PTR.
Would it increase 30 to 31?
Also close. So
Star pointer is the thing to which pointer points to.
star pointer is the thing to which pointer points to, so what is that? That's...
Pointer is pointing to 20.
Pointer is equal to 20, right? It's pointing to location 20, but what's at location 20?
10.
So this is
Pointer
10.
points to 10.
So star 10 is the thing at location 10. That's 100. And plus something says increment the value at something. This should increment the value here, and it should change this to a 101. I was going to say let's try it, but I'm kind of afraid. Let's try it. What do I have? I and J and pointer. We're going to get all kinds of compiler warnings, but I don't think I'm worried about that. J equals address I. Pointer equals address J. It's probably going to complain at me. Warning, warning, warning. Oh, I got an error.
Now the typewriter.
Oh, it doesn't want to do the plus plus.
That's the one.
Well,
It's pointing at pointer too.
let's just try star star PTR. Oh. All right, it's saving us from ourselves. Oh.
Softly.
Wow, that's rude. Well, okay, it's not going to let us have any fun. Anyway, the analysis still holds, but it's saving us from what it thinks is a bad course of action. Try one more thing. Yeah. So it So this works exactly as we analyzed, except the compiler is sticking its nose into our business, right? And it's saying, since I'm trying to dereference the thing that pointer is pointing to, pointer needs to be a pointer to a pointer. And so if I just declare it to be a star star, right, then the compiler's happy. But if we were, the type of the variable doesn't affect any of these operations, right? So if we were to just take the assembly language and assemble that and drop it in, right, it would work exactly the same. So, so you can get sort of arbitrarily crazy with these things. Fortunately, we don't have to for most of what we're doing. About the only time that we're going to, the most common time we're going to use stars and ampersands is when we're passing variables to functions and we want to get values back. And that's the whole call by value, call by reference business, right? C is always call by value. So if we want to change an argument, we have to pass its address. So we use an ampersand when we call the function, and inside the function we say it's an int star. And then if we want to change the value that it points to, we do something like, you know, star error equals 1. And that's probably the most common time we're going to encounter the star and the ampersand. And most of what we do is going to be using this to dereference and pick off a field. So the dash greater than arrow.
What's a star arrow?
This is an example. So if error is a point, so if you have a function and let's say x is an integer, you call your function, you pass the address of that integer. So in your function, let's just say it's called error. We declare it to be a pointer to an integer. And then if we want to set that argument to 1, we can say something like thing that error points to is equal to 1. And the result is when we come back here, this variable x will now be equal to 1. Whereas if we just pass x and we call this error and we say error equals 1, when we come back, x hasn't changed, because we can't change the value that we pass to a function. So we pass the address of a variable, and we use that to change the variable in a function. And that's why when you do scanf, you always pass an ampersand. If you have an integer, pass its address. All right, other questions about this or around this? So I've had some questions outside of class about the main program for PA1. So let me remind you what your main program is doing. So initialize your linked list, which is just a call to your init function. And then print out a prompt. And then read a line of input. So that's an fgets call usually. And then we're going to do the following. If the input looks like I followed by some number, then we're going to say add linked list comma number. If the input looks like search number, then we're going to call search linked list number, and so on. If the input looks like D number, then we're going to call delete linked list number. If the input is just P, then we're going to say print linked list. If the input looks looks like X, then we can just say return, because we're done with our program. So maybe these are all else's. Depends how you want to code it. Otherwise, if it's none of those, print out a little help message. Say, here's your commands, right? And then we're just going to go back up to the top. Print a prompt, read the input, process the input. That's essentially your whole main program. It doesn't do a whole lot of heavy lifting as far as manipulating lists, going through the array, saying this dot next equals that dot next dot data, etc., etc. None of that stuff. It's really just a bunch of function calls. So the hardest part of this are these lines about if the input looks like I followed by a number. So how do we write something in C to tell us if this variable input looks like I followed by a number?
You could use scanf.
scanf, yeah,
For 2 arguments.
with 2 arguments.
Then we separate it into 2 different categories. The single argument and the double 2 arguments.
There you go. So is input I followed by a number? scanf input, quote, I space %d, comma, address of number, and save the return from scanf in an integer like result. If result equals 1, then yes, input is exactly I followed by a space followed by an integer. And that integer value is in number, so we can just say add ll, comma, number.
Would the result be 2? Because you're...
We're only asking to convert one thing,
Oh.
so it'll actually return a 1.
Couldn't you do it both on one line? Or for both the character and the...
You can do a %c, %d, yeah, and then get the character like that.
Would it typically return a result equal to 2?
No, because we're only converting one thing and we're only storing one thing. So the return from scanf is the number of things that it converts. So we're only asking to convert one piece of the input, which is a number. Yeah. So do your add, save the result of this somewhere so that we can say if it returned 1, we succeeded in adding, we can print out a message saying success. Otherwise, we can print a message saying we couldn't add, and so on. And yeah, you can either do a %c, or if you just want to know what the first character of the input is, it's just input bracket 0. So you can do something like if input bracket 0 equals, quote, I. And if it is, then we know that we've got an input statement. So then we could do our scanf. Or you could do a switch on input bracket 0. And you could do case I, case D, and so on. So there's a lot of ways you can do this. Bunch of if statements, bunch of scanfs with ifs, switch statement, whatever works for you. But in the end, it's just a bunch of conditionals and calls to your other functions. So main programs, typically they call other things. Most main programs aren't going to be 1,000 lines of code. They're going to be, you know, call this, call that, do a loop, that kind of thing. At least for us. Yeah.
So scanf can look for specific characters like I?
Mm-hmm. Yeah, you can put in particular patterns of text in here, and it'll require that it matches that pattern. Spaces match any white space, and then percents match things like integers, floats, stuff like that. scanf is worth spending some time experimenting with because it's a real powerhouse of a function, and it can do lots of things that you want done sometimes. All right, so I will see you tomorrow.